So now relativistic field, I will just write down one Lagrangian, but we will not dig into the details because the relativity is I mean some of you are expert of it, but let us not get dragged into that details. So this will be the equation of motion. I mean I in fact derived it. Okay. Now you need to worry about plus sign, minus sign, and this basically the gauge, not gauge, metric. So we write the Lagrangian for a particle of mass m like that, and now field of mass m. So m is called mass of the field. Okay, we will worry about it later, but this is the term which is for a scalar field of with mass m is a parameter. Now this one means del phi del mu, we write dt phi square. I do not, so there is a minus sign, no. So if you recall, the invariant measured normally comes like that, delta t square minus delta x square. This is invariant measure del s square, right. There is a minus sign. So contravariant, covariant you multiply. So it is not a plus sign. In relativity, the invariant quantity, there is a minus sign for the time and space, there is separation, there is a minus sign. So same thing will reflect here. This is a product of contra and co. So I will get dx phi squared minus half m square phi square. Okay. So this is expansion in t and x. If you have y, then there will be y will also be there. Now if I just substitute it here, I will get this equation. I will leave it for you to do it, it is just straightforward. So we will get this is the fourth derivative which is written as that dt square minus Laplacian square. Okay. So this is in 1D is going to be d by dx, this is like that, but in 3D is going to be Laplacian. Okay, all of you know it, with double derivative with y, double derivative with z, they are all added up. Okay. So this is the equation of motion for scalar field with a mass parameter m. Okay, this m has come there, and okay, this is what we get. In fact, we derived Green's function for we derived Green's function for such fields in the past. Now, so this is Lagrangian. So for any field, we are given Lagrangian. From that I can derive equation of motion, and I can do other things as well. I mean once I have the equation of motion, I can derive the Green's function like what I did in the class. Okay. So we need to know that part and we quantize it, that will be quantum field theory. Now for fields we also write down Hamiltonian, the way we write down Hamiltonian for particles. Okay. So particles Hamiltonian is function of momentum and position. Lagrangian is function of, like for fields, Lagrangian is function of phi this and d phi x, but momentum the Hamiltonian is function of momentum field, momentum of the field, well momentum density actually, and position phi and phi. Okay. So this will be replaced by the momentum, this will be replaced by momentum. Okay. And this is called Legendre transformation. So we will have this momentum phi, and it could be also function of this gradient of phi. Okay. So this Hamiltonian will be function of these quantities. Okay. So let me just briefly tell you how we construct Hamiltonian, and we need that for our course. Okay. So first we define momentum density, like we have phi is function of x and t. Similarly, momentum will be function of x and t, is a momentum density. Okay, it is not momentum. So every position will have momentum density. So that is defined as delta L delta phi dot. Well, right now we have field has only one component, but there could be field with several components. Like velocity field has 3 components. No, so right now we have only one component. So it is this object. Okay, basically I made a mistake. This is density is this quantity. Okay, Lagrangian density, take the partial derivative with relative to phi dot. just focus on equate these two. This is connected with the total momentum, okay, but we ignore that. So, then we define Hamiltonian, pretty similar to what we do for particles, momentum multiplied by phi dot minus Lagrangian density. This is Hamiltonian density. If you recall, for particles, how do you write Hamiltonian? H is P I x I dot minus L, sum over all i's, right, or that is a generalized coordinate we do it. So, it is, look, P is replaced by momentum density, x I dot is replaced by phi I dot. So, I are components, okay. I mean, as I said, right now we have one component in illustration, but I could have more components, minus Lagrangian density, okay, straightforward. So, and total Hamiltonian is integral of Hamiltonian density, okay. We also write typically as d cube x h in 3D, in 1D it will be just dx, okay. Now, equation of motion for particle, we know how to write that, right. X dot is p for 1D and p dot is, no, x dot is delta h, I am sorry, delta h by delta p, delta h by delta p, and delta h, and p dot is minus delta h by delta x. So, we do follow exactly the same procedure. Now, here h is a function of pi other stuff. So, we write this variational derivative, functional derivative, okay. So, inspired by that, and pi dot is functional derivative of h with phi, okay. So, this is what how we define it, okay. So, let us work it out. Is that clear, the formalism to everyone? Is just, if you know for particles, then you can just translate it. I am doing it a bit fast, but you just translate that. So, I derived this now for string phi dot square, this is time derivative minus that one, minus v phi. In general, like we had m squared phi squared for one example, I could have, by the v phi I could write as phi squared minus phi 4. So, this is a potential. So, potential we write as x squared minus x 4 for particles, or x 4 x squared minus x cube. So, here we encounter potentials of this sort, okay. Now, you have seen this potential somewhere, okay. So, the free energy in phase transition, Landau theory, if you done stat mech, Landau theory, the free energy has this form, okay, and that is where we get this phase transition. So, we will see this is called phi 4 theory, okay. This is a phi 4, 5 to the power 4, and it plays a very important role in many phenomena. So, potential is function of phi, okay. So, now let us write down the Hamiltonian for it, okay. This is given Lagrangian, I can convert to it Hamiltonian. So, what is pi? Momentum density, partial L, partial phi dot. Well, actually I am carrying this I is 1, okay, I is. So, what is partial L, partial phi dot? I will get from here, right. Derivative of with phi dot is just phi dot, right. Square, the 2 will cancel with half, just phi dot. Now, once I get pi, then I can write down the Hamiltonian by this formula, pi phi dot minus L. There is only one field, so I do not need to do a sum. So, pi phi dot will be, pi is phi dot, another phi dot square minus this Lagrangian. So, Lagrangian has half phi dot square, the minus grad phi square half minus v phi, okay. So, phi dot square minus half phi dot square is this object, this minus becomes plus, is the potential energy. Well, not we make a change, this grad phi is like a some kind of tension coming from that, okay. So, this is, I had told for string we call this as a potential, but in field theory these kind of terms are called potential, okay. This is potential, okay. Grad phi is intuitively you can think of that as potential also, but this notation keeps changing the definition, okay. So, this is coming from here. So, I hope it is clear, but this is Hamiltonian, but not yet, because Hamiltonian should be function of phi, this one, and potential, sorry, momentum density. So, this is not function of this should not be here, right, but I know what phi dot is. Phi dot is nothing but pi. So, this one becomes that, and remaining two terms remain as is. Okay. So, that is our Hamiltonian. Now, given Hamiltonian, I can derive the equation of motion. So, I wrote that, no, d phi dt is functional derivative of pi with h with pi. So, here is straightforward, is just going to be the right hand side will be just pi. So, phi dot is pi. Okay. Straightforward. Next, pi dot is functional derivative of h with phi, functional derivative and is not the simple derivative. So, functional derivative, recall I had to perturb the function by delta function and subtract and do all that operation, which, so it is a reasonably complex operation, but you need to do that. If you do partial derivative, I will get only this term, right. So, that would have given you only this term, but because it is a functional derivative, there will be a contribution from here as well. If I vary phi, then grad phi also will vary, right. I put a delta function to phi, so the gradient also will get some kind of perturbation, and that contribution comes here. And recall what I did when I do the by parts, I will get a minus sign and divergence. Okay. So, all these things are done by parts, and the surface term vanishes, and because we let it go to infinity when I do the integral, and I get that term. So, this part will give us minus dv by d phi, this one. So, I can take the, it called total derivative. Okay, I do not need to write. So, v is only function of phi, and this one gives us v, and this one is what, partial h partial grad phi is just grad phi. So, that, so I get this object. Okay. Now, this is pi dot. So, I can use this one, replace pi by phi dot. So, this becomes phi double dot, right, or this is dt d phi. Okay. So, that will give me the equation of motion for the field. It is this. Earlier we did not have v, and basically we had this equal to that, but now with v this is what we get, Newton. Okay. For relativistic field, this was, it came as minus m squared phi squared, minus m squared phi, sorry, minus m squared phi. Okay. So, given Hamiltonian, I can also derive the equation of motion. Okay. So, this is a simple example, but we will go to slightly more complicated example, Schrodinger equation. Okay. So, Schrodinger equation is a psi is a field. So, we can also write down the Lagrangian for Schrodinger equation or Lagrangian for psi. Schrodinger equation will be derived as the equation of motion. Okay. So, for this, the Lagrangian is written like that. You may, this may be guessed, it is coming from the Laplacian term, no, this will give you Laplacian, this will give us v psi, but this term is give you what, is a IH bar d by dt of psi. Okay. So, this looks reasonably complicated, I by 2 psi star psi dot minus I by 2 psi dot psi star dot. These are time derivatives, huh? This is dt is psi. Okay. Now, let us try to derive the equation of motion. Okay. Now, whether this form is required, well, I am going to do that next set of slides on Noether's theorem. This is a good form for Noether's theorem, but this is not good form for equation of motion. Okay. So, I need to convert this for equation of motion. Okay. So, I can always add and subtract d by dt of a some function f, right. You know that, no, for particle dynamics you can always add total derivative of a function, total time derivative of a function, that because my action does not change because I have d by dt, df by dt and So, f at the end points is this will give you 0. Okay. So, you can always add and subtract. So, here I can add in fact basically subtract add d by dt of psi star psi. If I do that, then I will get, in this you just add. If I do that, then you can see that well half, put half here. So, if I do that, one term will cancel, psi star dot, okay, and I will, well this is in fact add is plus half of that. Okay. So, one term will cancel with that, and you the first term will get amplified, and we basically get that, okay, half plus half. So, I psi star psi dot minus this term and minus that term. Okay. So, this is Lagrangian for a particle for the field, not particle, Lagrangian for the field, that will give me Schrodinger equation. So, let us start doing that stuff now. This is Schrodinger equation, non-relativistic. So, the first term partial derivative of Lagrangian density by psi star. So, what will that give me? This one. So, take the derivative, psi star appears only, it appears here as well as here, right, two places. So, the first term will give us what? I psi dot here, and the other term will give us minus v psi. Okay, this is this term. Now, there is nothing called d by dt of psi star in this equation. No, there is a term here, dt psi star. No, there is no term, dt psi star is not there. Okay, right. This is psi dot. I remove that dt psi star dot, right. There is no term which is psi star dot. I removed that by this trick. Okay. So, I will get contribution from here. So, what will that give me? It will come from here, no, d partial derivative L with partial psi star x. Okay. So, that will give me grad psi or d by dx psi by this object, and I take another derivative, I will get that. Okay. So, this term gives me minus half 2m grad square psi. Okay. So, this equal to that, and that is this equation. So, this is Schrodinger equation for field psi. Okay. Lagrangian is this, and we need this Lagrangian in future. You can also derive Hamiltonian. Okay. So, this I will leave it for you to work it out. Okay. So, we just follow the same procedure, and this homework, you should do that homework at Hamiltonian. Now, from Hamiltonian, can I derive Schrodinger equation? This is Hamiltonian, I should be able to derive Schrodinger equation. So, let us do it. So, this is my Lagrangian. From that I can get pi. So, partial L partial psi dot, which will give me I psi star, right. I mean, this will act here and I get that. So, momentum density is I psi star. Then next I apply pi dot is partial h partial psi. So, partial h partial psi will be coming from this term, which is that, and I will get from here. In fact, it should be not partial, it is functional derivative, no? Functional derivative. So, that will give me this from this one. Okay. But pi dot I take pi equal to I psi star. So, this is going to be I psi star dt, like that, okay, coming from here. Now, there of course is function of psi stars. So, take a complex conjugate of the equation. What will I get if I take the complex conjugate? I becomes minus I, this will become change sign. So, let me do it here, minus I dt psi equal to V is a real function, no? So, V does not get complex conjugate. the minus sign. Okay, no, this correct here, minus I star and minus I plus half 2m grad psi. Okay. Now, there is a minus is off by minus, no. So, just put minus 1 multiply both sides, I h bar h bar is 1 for me. Okay. H bar I am not carrying around, that is minus 2m grad square psi plus v psi. So, this is equation for this Schrodinger equation. Okay. So, we can derive this for both Hamiltonian, well there is a minus sign, I made a mistake. So, we can do it from Hamiltonian as well as from Lagrangian.